In the last video, we considered the situation where our characteristic polynomial for solving a second-order homogeneous linear ODE produces repeated roots. So we get basically R1 and R2, but they're both the same, and both of those equal, we'll just call them R, so we don't have to keep distinctions between R1 and R2 because they are exactly the same. So the question is, why does this work, right? Because we showed what would happen if it did work. If we just put a t in front of one of those e to the rt's, why does this magically solve the problem? How do we know that this isn't just some arbitrary made-up thing? And the way we could always prove that something is in fact a solution is by showing that it works for the differential equation. Now the question is, when do we get repeated roots? Right? Like, what structure of second derivative plus something y prime plus something y equals 0? The question is, what are these coefficients going to look like in the event that we get repeated roots? Well, let me start off by getting us to recall that we're always guessing something of the form y equals e to the rt. And the first derivative is r e to the rt, and the second derivative is r squared e to the rt. And when we plug these things in, r squared e to the rt for the second derivative, plus, we get whatever this quantity is going to be. We're going to figure these out, what's in the box. But this will be r e to the rt. This will be plus something e to the rt equals 0. And what we find out is that these coefficients of the e to the rt's, right, because we have an e to the rt, another e to the rt, another e to the rt, basically r squared plus that something times r plus that other something, that needs to equal 0, right? And in the case of repeated roots, okay, let's say that we do get repeated roots. Well, when does that happen? Well, that happens anytime we get a situation that's like r plus 1 squared, that we could factor the quadratic into a perfect square. Okay, in this case, this would be r squared plus 2r plus 1. Or, and if you set this equal to 0, you just get r equals negative 1, right? Because r plus 1 times r plus 1 equaling 0 means that either the first factor or the second factor is 0, and that'll only happen if r is negative 1. For r plus 2, we would get r squared plus 4r plus 4. For r plus 3 squared, we would get r squared plus 6r plus 9. Now, what's the relationship between these two values here? 2 and 1, 4 and 4, 6 and 9. Well, let's write it this way. R plus c squared, right? So our root is always the negative of what's in here. So in this case, r would be negative 1. This is r equals negative 2. R equals negative 3. This would be r equals negative c. And if you FOIL this out, r plus c times r plus c, you get r squared plus 2cr plus c squared, right? Because when you FOIL, you get r times c. You get r squared plus rc plus cr. Well, rc and cr are the same thing, so it'd be 2 of those. And that gives us the middle term, and then plus c squared. Okay, so that's what we would expect to see in this polynomial if, in fact, we were going to end up with repeated roots. So one thing I want you to notice here is that if you take half of this number, okay, if you focus on this number right here, if you take half of that, well, what's half of 2c? Well, 2c divided by 2 is just c. So if you take half of this number and you square it, right, because then you get c, and you square that number, you should get this number right over here. So here, take 2. Divide that by 2, you get 1. 1 squared is 1. Take 4, divide it by 2, you get 2. 2 squared is 4. Take 6, divide it by 2. That's 3. 3 squared is 9. So that's the relationship between the coefficient of the linear term and the constant when you end up with a single root. Okay, so that would mean that whatever our root is, so our root is r equals negative c. In that case, we would expect to see 2 times c here, and we would expect to see c squared over here. Now, what I want you to think about here is be careful, because c itself could be a positive or negative number. All we're saying here is that this c is the opposite sign of whatever this c is. So r doesn't necessarily have to be negative. It's just whatever r is, this c value here will be the opposite sign of it. And this will be, well, it's a square, so it doesn't make a big difference. Okay, with that said, well, now we know what our differential equation would look like in the case that we get a repeated root in general. So this would be a 2c, and this would be a c squared. Where, you know, if we found out that if we cut this number in half and squared it and got this number, then that immediately would tell us that our root is the opposite of that number. So here in this case, let's go back to this. Take half of 2, you get 1. 1 squared is 1. That means our root is negative 1. Here, divide 4 by 2, you get 2. Square that, you get 4, so r is negative 2. It's always the opposite of what you get when you divide this by 2. That's all we're saying over here. Okay, so this is the equation that we expect to see when there's going to be a repeated root. The reason this is important is because now we're going to claim that the solution is y equals k1 e to the ct plus k2 t e to the ct. I'm sorry, the root would be negative c, right? That has to be a negative because the root itself is negative c. Okay, now what we have to do is just go through and prove that this, in fact, will solve this equation, that the 3 terms here on the left side will cancel out and give us 0. So we're going to have to get the first and second derivatives of this. This does require a little bit of thinking, because here we're going to have to use the product rule. We have one function of t times another function of t, so we can label those as f times g. But when we take the derivative of the first term, we should get negative c k1 e to the negative ct. Now, product rule f prime g, derivative of k2t, remember k2 is just a constant, so it'd just be k2, times the original g, plus fg prime. So k2t times the derivative of g would be negative c e to the negative ct. So I'll just pull out that negative c, and make this negative c k2 t e to the negative ct. So I've just implemented the product rule on that. And I have to take the derivative of that to get the second derivative, so I can plug these 3 functions back into our what we know would produce repeated roots and show that it solves the equation. So the second derivative would be first term c squared k1 e to the negative ct, because remember now we get another factor of negative c, and negative c times negative c is c squared. Positive, right, because we're multiplying 2 negatives. Here we would get negative ck2 e to the negative ct. And then here we kind of get a similar thing as we did with these 2 terms. It just kind of keeps on expanding. Let's just call all of this, we'll call that f, and then we'll call this piece g. So f prime, negative ck2 is just the coefficient, right? Those are just 2 numbers multiplied together times t. That would just give us negative ck2. Times the second, times g. Sorry, this should be what I'm doing here. And then we have f times g prime. So g prime would be negative c e to the negative ct times negative ck2t would give us negative c times negative c is positive c squared k2t e to the negative ct. So just got to do some bookkeeping here. And now we were claiming that the equation that this solves is one that looks like this. Plus c squared y equals 0. So now what we need to do is we need to plug in the original function. Here we're going to plug that, I'm sorry, not that one. It's in a different color. We're going to plug in second derivative here. So c squared k1 e to the negative ct minus ck2 e to the negative ct minus, oh, by the way, we get, notice that these two terms are exactly the same, so that means we just have negative 2 of them, and then plus c squared k2 t e to the negative ct. Okay, that is all just the second derivative being plugged in for the second derivative. Plus, we get 2c times y prime. Okay, so we have to take y prime and we have to distribute the 2c into that. So 2c times negative c would give us minus 2c squared k1 e to the negative ct. All I'm doing here is just distributing this into the parentheses here. Now remember, this is a negative c. This is the opposite of whatever this is, so we should still have a negative sign. And then when you distribute it here, you'll get plus 2c k2 e to the negative ct. And then when you distribute it here, you'll get minus 2c squared k2 t e to the negative ct. And now we need to add c squared y to that. I'll do that in purple. So for y, we need to plug in this whole thing, right? So now we're going to, I should say this whole thing. Now we're going to multiply c squared by this term and by this term right here. It's getting a little messy. But we get plus c squared k1 e to the negative ct. And then when you distribute c squared here, you'll get plus c squared k2 t e to the negative ct. And what does this need to equal? Well, this needs to equal 0, right? In order for this to work out. So I'll put a question mark above the equal sign, as we always do, just to see what we're verifying. Now, anywhere I have a k1 e to the negative ct, I have a k1 e to the negative ct here. I have c squared of them. I have a negative 2c squared k1 e to the negative ct right there. So here I have positive 1 of them. Here I have negative 2 of them. And if we look a little bit further, right here, we have another positive 1c squared k1 e to the negative ct. So here we have positive 2c squared k1 e to the negative ct minus 2c squared k1 e to the negative ct. Guess what? These all cancel out. So far, so good. Now here we have negative 2c multiples of k2 e to the negative ct. This one has a t e to the negative ct, so I've got to be careful. That's not the same thing. Here I have plus 2 ck2 e to the negative ct. So that's k2 e to the negative ct. The other ones have c squareds in them, but if you look at it, this is a minus 2, this is a plus 2. Same terms, opposite signs, they cancel out. Finally, here I have a c squared k2 t e to the negative ct. Here I have another c squared k2 t e to the negative ct, but here I have minus 2 fewer of those c squared k2 t e to the negative ct's, and guess what? Those cancel out, and on the left-hand side we have 0, and 0 equals 0 is a true statement. Therefore, our claim that when we have repeated roots, this is the general solution is in fact valid. Now we needed to do a little bit of thinking and a lot of algebra here to think about, well, what will our equation look like in general form when we are supposed to get repeated roots? And we had to start off kind of battling with that a little bit. But once we knew that, well, then we could plug this in. We couldn't really plug this in general, right? Because this doesn't work when there are two distinct roots. This will only work when there are repeated roots.